How is it that that second function generates the points in a way different than the first one does? Think about calculus. Think about calculus. What's different about these two? The rate, right? The rate at which the points are generated for changing t. What's dx dt here? 100. What's dy dt? 200. No, whoa, that's not even close. What is it? It's 10,000 t squared, 20,000 t. Did I do the math right? No, but the function is 10,000 t squared, right? No. 100t squared is 10,000 t squared. 100t quantity squared is the function 10,000 t squared plus 1. So therefore the derivative is 20,000 t. What's the derivative up here? dy dt is? Same function or different function? Much different, right? So for a change in t, what happens? We get a huge change in y versus the original. 20,000 times whatever the value of t is versus twice whatever the value of t is in terms of your change in y. So the second function, it produces the same points, but it does so in such a way that for a change in t, you get a much, much bigger change of x and y than you do the original way, with the original function that it had. So it's, for a change in t, it's sweeping out much more of the curve for the same change in t than that first one did. Okay, questions on 70? 72. The lower half of the circle centered at -2, 2, radius 6, oriented in counterclockwise direction. Okay, so we worked on these in web work. Let's just do it one more time. So we want, let's write the x equation first. It's going to be x minus 2 squared plus y plus 2 squared equals 6 squared. So we want to write the lower half oriented counterclockwise. So first let's just write the whole thing. So we know we want to get something in the form like this, so that this could be sine or cosine or negative sine or negative cosine, so this would be x minus 2 over 6. Can go in there, and y plus 2 over 6 could go in there. So what am I? I'm dividing by 6 squared, and then I'm making expression squared, right? Divide by 6 squared, then x minus 2 over 6 quantity squared, and y plus 2 over 6 quantity squared. So then the question is, what do I assign? Sine, cosine, negative cosine to get counterclockwise. So if we did x cosine and y sine, this would be associated with the standard definitions of cosine and sine, meaning x and y coordinates as you go counterclockwise from 3 o'clock, right? So this would give counterclockwise orientation, and that's what we want. So when you assign x to be positive cosine and y to be positive sine, you're going to start at the 3 o'clock position, and you're going to go counterclockwise. That goes back to the definitions of cosine and sine. Since we want it counterclockwise, we can just leave it like this. Now we want to get the lower half of the circle. Oh, so now we have to define the function. So x is going to be 6 cosine t plus 2, and y will be 6 sine t minus 2. And if we want, so at t equals 0, that's going to put us at 2, negative 2, radius 6, so I don't know, something like this. So this will start us here at t equals 0 and take us around counterclockwise, just like the original definitions of sine and cosine. So if we want the bottom half of the circle, what angle could we choose? T from? We want to go from here to here. So there's an infinite number of ways to do it. The most basic way would be T from what to what? Pi to 2 pi. Is the bottom half of the circle in the first rotation, right? In the first rotation, that's the bottom half of the circle. So what else could we do? We could also do T from 85 pi to 86 pi. Is that right? Is that good? Is that? Yeah, that's right. So I could go around as many times as I want, as long as I start on the left-hand side, which would be any odd multiple of pi, and end up on the right side would be any even, the next even multiple. That would give me the bottom half of the circle. So I can go 3 pi to 4 pi, 5 pi to 6 pi, etc. So I'll go from 85 pi to 86 pi. That would give me the bottom half of the circle. Is there a question?
Should it be x plus 2 squared then y minus 2 squared?
No, because I'm going to add 2 to both sides to solve for x.
No, I mean at the very top of your equation. The center of your circle is at 2, -2. Not
Okay, well that's the problem I did. I'm not going to change it. Did I do the wrong problem? Okay. So why didn't you tell me at the beginning? Okay. So I made mine centered at 2, -2, and that wanted it centered at -2 too. Okay, so you're just going to change all the signs of the. So it end up being -2 to actually do the problem 72. This will end up being -2 and +2. But I did it for my center as 2, -2. That's what I have written up here. Okay, also, what? This could be any function of t, as long as it's the same in both. It'll generate the same. Is that right? No, that's not quite right. Just stick to t. All right, we'll just stick to t. So if I start messing with this, then I'm going to have to mess with the interval as well. Okay, if I start messing with and do this like 3t and 3t, then to get the bottom half of the circle, I'm going to have to adjust what I did here. So we'll just leave it as t. But there's lots of ways to get this. Lots of ways to get counterclockwise around the bottom of the circle. Questions on 72? Okay, so let's talk about some things here. So I wanted to show you this. Here's an example of a parametric function. X equals 5 cosine t minus cosine 5t, and y equals 5 sine t minus sine 5t. And what that actually is the function for is, so I've got this circle, and then I've got this other circle, which is actually going to be like a wheel, and it's going to turn. It's as if you were turning that smaller wheel around on the surface of the larger wheel, and you were tracking a point on that smaller wheel. This parametric function would model that. Okay, so that blue function is the tracking a point on a wheel that's turning along another larger circle. This is called an epicycloid. Okay, something that you could not do with y as a function of x, or certainly not easily. But you see that the parametric functions aren't that complicated, right? The parametric functions aren't that complicated. Just these x and y equations here that are relatively simple compared to if you tried to write that. It'd be very difficult and messy to write y as a function of x, and would take multiple equations to do it. Okay, so here's an example of how the parametric equations are much more suitable to this type of curve. Okay, and so what is t? T is some angle, right? So t is like in your example of the plane example in your homework. T represented time, and so you got ordered pairs on the plane as a function of time, and that's a prevalent use of parametric equations. But here, t is not time. T is the angle. T is the angle swept, I think counterclockwise from 3 o'clock. It's like the standard trig angle, and then it generates the xy ordered pairs of this point on the wheel as it turns around the bigger circle. So that relates to your project, which is due a week from today. Hopefully you've at least looked at it. And it's Clara and the silo. Okay, Clara is the calculus cow. So Clara here is the silo. You're looking down on the silo here. You're looking down on the silo, which is 2 meters, has a 2 meter radius. Okay, 2 meter radius. And so Clara is, she's tethered to the silo by a rope. So one end of the rope is tied to Clara, and the other end of the rope is tied on the leftmost point, or the westernmost point of the silo. And so, and the rope is just long enough for her to get to the easternmost point. If the rope wrapped around the silo like that, she could get to just exactly to the easternmost point. And so the question is, what's the boundary of what she could graze? What is the boundary of what she could graze? So it looks like this. So she's keeping the rope as taut as she can. And then that would continue around the bottom, but we'll just focus on the top half. So this would be like the boundary of where she could graze around the silo. So the project is to determine a parametric function for this curve, and then figure out the area, the total area in which she has to graze. Okay, and so this is a nice, challenging yet attainable project for where we're at in the course. So it's going to take some thought. It's going to take some work. You're not going to sit down and do this in one sitting. You're going to have to work at it and think about it, and then maybe get a little help, and then return and work at it some more. But if you work at it, you can get it. You can get it. Again, here, this is not, the parametric equations will not be functions of time, but will be functions of theta. So let's look at the actual project that I posted. But this is a real nice question that's difficult but attainable. That's what we got here. So if you haven't looked at it already, let's open it up. So Clara and the silo. Clara and the silo due a week from today. All right, so there she is. Oh, and so then it's going to be really helpful if you have a standard TI. Most of you do. And you're going to use the parametric function on the TI. So to get the parametric function, you're going to go to everyone. If you've got it, go ahead and get it out. Thank you. So you're going to go with the mode. Hit the mode button. And on the mode button, you can choose there should be at the row. Which row is it that allows you to choose parametric functions? Like the third or fourth down? Fourth? The fourth row down, you want to change your function to parametric. And you put the selection on parametric. Then when you hit the y equals button, it's going to let you put parametric function. It'll do x1, y1, x2, y2. You can put parametric functions in there. So go to y, set its parametric, then go to y equals. And you'll see that. You'll see that now you're entering parametric function, right, as a function of t instead of x. X is a function of t, y is a function of t to create a parametric function like we've been working on. And then if you hit the window, if you go to window button, so it's going to, not only is going to ask you for the x and y like before, x min, y min, the window. So the window will still display x and y coordinates. That's like what we've been doing, right? The graphs are still x and y, but now x is a function of t and y is a function of t. There's something called t-step. So t-step is, it's basically asking you what points, how many points you want it to plot, or how often do you want it to plot a point and then connect the dots. So it's going to create that curve by generating several points according to your t-step, and then just connect the dots. Okay? So you notice that you need a interval for t, an interval for x and y for the display, and then a t-step. So I'm telling you that here for the first function, which is a very easy startup question, which is just to graph the circle for the silo. Okay? Just parametrically graph the circle for the silo. Okay? So the progression of questions is such that you want to make sure you're 100% sure on what you've done on a question before you move to the next one. Don't do one question halfway or be kind of unsure, because if you get it wrong, then you won't really be able to proceed. So make sure you fully exhaust your understanding that you've got a particular question before you go on. Okay? So let's look at, in order to get the parametric function for for that boundary around which she can graze, keeping the rope taut as she moves out around, I've given you this very helpful setup. Okay, and so the parameter t is this angle theta. This is the t. This is the t. It's not time, right? So not all parametric equations are functions of time. I showed you the epicycloid. This one as well. Your parameter, x is going to be a function of theta, and y is going to be a function of theta. And so you're looking for the x and y, you're trying to generate the x and y coordinates of this point right here, point P, which is it represents any point on that curve that she sweeps out as she keeps the rope tight, right? Keeps the rope tight. And that x is a function of theta and y is a function of theta will be those parametric equations for that curve. So this will take a little work and thinking and several sittings. You're not going to sit down and do this project at once, okay? So that setup is going to be very, very helpful for you to do that. So on your calculator, x1 and y1 will be the silo. x2 and y2 will be this interesting curve of her peeling the rope off and keeping it tight, the boundary around which she could graze, or within which she could graze. And then you'll keep proceeding. There's 2 pages to the project, okay? Any questions? What's that? What's the t? T is this angle theta. Is that what you're asking? Yeah, this angle theta, which is swept to where the point where the rope is peeling off. See that? So that angle theta is not the angle from the center to the point P. You see that? It's the angle to where the rope is just starting to peel off for any given angle. Okay? So it's right where that rope is starting to peel off on the circle. That's the angle theta. It's not the angle swept to the point P from that from the center of the silo. So make sure you're aware of that. Other questions? Okay, so you definitely want to get going on this. So if you need some help, you can get into office hours. Remember, our office hours are Tuesday, Thursday. So, and then you'll have the weekend to finish it up. We'll turn it in Monday morning. Okay? And then, so some of you have asked about extra credit. So if you do a particularly good and professional job on this project, you could be in the running for some extra credit in the course too. Okay? So we'll make it out of, it'll be required for everybody out of a certain number of points, and then we'll say that if you do particularly well, you can get more than the total amount of points. Okay? And remember, there's 2 pages to it. 2 pages. Okay. Any questions on the Clara project? Okay, so let's talk about area. So one part of that project will be, how much area does she have to graze in? How much area can she reach in that setup, in that context? And so we want to talk about area. So if y is a function of x, how do we find area? How do we find area? Yeah, so at the beginning of the course, we really focused on integral as what? An amount of accumulation, or amount of total change, right? Knowing the rate of change, right? We looked at integrals as, we've got a rate of change curve. We want to know how much total accumulation or how much total change in the quantity is there. All right? And so then we said, but there's another alternate way to look at integral, and that is through the lens of area, geometry. And we spent a lot of time on that as well. And so we said that this area was the integral from x1 to x2 we said rate times a little amount of change could be represented graphically as height of a rectangle times a little width of a rectangle. That it was kind of, because of our coordinate system, that little bit of change could be represented as the rate or the height of the rectangle times a little change or the width of the rectangle. And so instead of little bits of change, we could also see these as areas of thin rectangles, right? Areas of really thin rectangles. And then the integral was sum, right? Sum up the areas of lots of little thin rectangles as you go from left to right, x1 to x2, gives us that area under the curve. And then if that curve went below the x-axis, that would have a negative effect to the total area. So it's actually, integral actually computes a difference of areas, right? Difference of areas between where the areas are above and below the x-axis. So we want the same thing here. How do we do it with parametric curves? All right, so here is t equals -1. So I'm interested in, suppose I'm interested in for whatever reason, let's see. Does that show up on the screen? Good. Okay. Wherever reason I'm interested in this area right here. I want to know the area from this, starting at this intersection point, to t equals -1 above the x-axis. Right there. And where I'm stopping here, there. Okay.
Isn't
What's that?
that line up?
Yep, it is at x equals -3. So what's that? What did I tell you? That's t, right? So when t is -1, you get x at -3. Yeah, so this is t, not x, right? So t equals -1. Okay, so we're going to look at, so when we have parametric functions, we don't have y as a function of x. We have like x as a function of t and y as another function of t. But what we do is it's gonna be parallel to this, exactly parallel to this, right? So what is f of x? What is f of x? F of x is just y, right? And what is dx? So this is y is now g of t. It's going to be the height. It's going to be our height from the x-axis to the curve. That's what f of x is. Now it's g of t. And what's dx? Well, if x is f of t, then what's dx? Dx is f prime of t dt. Like a little chain rule there, right? It's going to be the derivative of that function with respect to t dt. Then times the derivative of differential of t. So we've got what we need to, we're going to rewrite this now in terms of t. What is f of x? F of x was y, so we still want y. What is y? G of t. So we're still doing y dx. Just like we did when we did rectangular coordinates. Y dx. So y is now gt, and what is dx? F prime of t dt. So we're operating in parametric in coordinates with respect to t, but we're still seeing that, thinking of that as simply y dx or f of x dx, like we did before. So it's generating area in the same way, vertical thin rectangles from the x-axis. But it's now just in terms of t, and then we're going to start from, say, t1 to t2. So, and that's going to give us what? Difference of areas. Just like it did before. Difference of areas where our baseline is the x-axis and our rectangles are up and down from the x-axis to the curve. So to do this then, to get this area, we'd simply need to get that t-value, which would be, how would we get that t-value algebraically? If we needed to get that t-value algebraically, how would we do it? How could we get that t-value? It'd be the t such that what? Y equals 0. So it'd be a t-value, there's more than one. A t-value such that y equals 0. So you take that, your y equation, set it equal to 0, and get this t-value. And I'm going to just use technology to save time. Also, we don't know how to quickly get the roots of a quartic. Oh, I hate that. Are we still running with the video? Yes. Okay. So we got our area is going to be T1 to T2 of Still y dx, but that is the y function with respect to t times f prime of t dt. Okay. So we got t is negative 1.6, 0.08. And this was the point t equals negative 1. So it's going to be the integral from negative 1.608 to negative 1 of what's gt? That's y. I'm going to distribute the negative. Right, so that's gt, or y equals gt. F prime of t is 3t squared minus 6t dt. And what is this? This is our dx. dx is f prime of t dt. Okay, so this is kind of a little bit long and tedious, but easy, right? A little bit long and tedious, but easy. We'd multiply to do this the easiest way. We're just going to multiply out those two polynomials, get all the terms. Antiderivative of polynomial is easy, and then evaluate from negative 1.608 to negative 1. So tedious but easy, and then the number that we get would be that area. Okay, so let's predict it and then check it. So this is the point negative 3, 6. So if we made our rectangle out of this, what would the area of this rectangle be? This is negative 3. So we're at, this is about negative 11 about. All right, so what would the area of that rectangle be? Do it fast. This is y equals 6. What's a quick estimate of the area of that total rectangle? 48. 8 times 6, about 48. And then so what would you guess? Make a guess. Tell your, have it, make this a game with the person next to you. Who can guess what that area is? Who can be closer? All right, and I'm going to put in the integral as you do that. Okay, take a good look. To put it in, I have to take the picture away. So take a good look. Everyone, make your bet, and we'll see who's closer. Here. Okay, here's the moment of truth. 29.8. Who said 29 or 30? If you said 30, that was a good guess. 29.8. 29.8. Questions on basic area? Okay, so now kind of a cooler question and figure out what's going on here. So look at this now. What if I took the integral from here, t equals negative 1, to this intersection now? which is t equals 1.45. What is that going to give us? So I want to do that's the same integral from -1 to don't want to give it away though. So this is that's gonna be 1.45. Okay. So if I integrate the same thing from -1 to 1.45, what in the world will that give us? Why? Because the curve comes out to the right, but then it comes back to the left. It comes back to the left. So what area will we get for this integral, t from -1 to 1.45? Let's write it in up here. So the way that we can figure out what's going to happen is, let's split it up into the integral from t equals -1 to the rightmost point. How do we get the rightmost point again on this curve? What are we going to do to get the rightmost point? We should know, if we remember from Friday. Rightmost point we could identify. So we want, is it going to be dy dt or dx dt? We want no horizontal change. At the moment where there's no horizontal change or a vertical tangent, we know we're at the far leftmost point. And that's where dx dt equals 0. I think we did that last week. What was that value? Dx dt equals 0 gave us t equals. So we found dx dt, we set equal to 0, and we got 2 roots. And what was that one? 0. T equals 0. So the nose of our anteater friend here is at t equals 0, that the left side of him. And so if we can figure out what that will be. So if we go from -1 to 0 of gt f prime of t, so what I'll do is I'll shade that in red. Say. Hey, thank you. Yes, that's important. It's part of the math. So I'll do that. Since I wrote the integral in black, I will shade that in black. So that's straightforward, right? We know we'll get the area below that part of the curve down to the x-axis. Watch. And then down here, it'll just be bounded by the vertical line. Looks like x equals 1. Okay, so the black integral will give me that black shaded region. Are we good? Now, if I do the integral, I'll do blue. If I go from t equals 0 to 1.45 gt f prime of t, what will that give me? So that will be going starting from here to here. But what is the x value doing? As we go from t equals 0 to 1.45, the x value is what? Decreasing, okay? So it'll be this area here, blue. But because we started at a greater x and integrated to a lesser x, what will it be? What will we get if we integrate from 0 to 1.45? We're going to get the opposite of that area. Why? Because our x1 was here and our x2 was here. So this is going to be the opposite of the blue area. Because we're integrating to the left. We're integrating from x1 to x2, which is x2 is less than x1. Opposite of blue area. Black area is fine. It'll be positive, right? It'll be the positive area. So what will we get if we integrate from 0 to 1.45? Then what will happen? We'll get the total black area plus the opposite of the blue area. What will it give for us? Do you see what it will do? So now the integral from negative 1 to 1.45, which is the sum of these two, will be what region? Do you see that if we have all this and subtract this, what's left? So it's like we're subtracting, right? It's like we're adding all the area as x moves from left to right, and then we end up subtracting all the area as x moves from right to left. And we're left with the area inside the curve, right? So it's the area inside the curve. It's the area of the anteater's face. So we'll get the area inside the curve above the x-axis. So below the top and above that bottom where it's heading back to the left. So let me put it in. So I was going to do a little prediction game with you on this as well, but that ends up being 10 square units. That red area is 10 square units. It's what you get when you integrate all the way from negative 1 to the 1.45 at the intercept. Wherever x is going from right to left, those areas get subtracted out. And wherever x is moving from left to right, you get the standard area like we've done before. So in this case, you get the area inside of the curve. Inside of the curve. Okay, there's web work that's already been up for a while. Due Wednesday. And then you get started on your project.